And so then this is a nice special case for constant temperatures. And we should also mention our units of entropy. They're going to be units of heat over units of temperature. So that'll be in joules over Kelvin. All right. So with this concept in play, then what we can do is we can talk about the second law of thermodynamics. Okay. And what it talks about is that the total change in entropy or you could state it's the entropy change of the universe. So the total change in entropy never decreases. In any physical process. Okay. And so the way that they will write this, that delta S total is always greater than or equal to 0. Put it here. And it's equal to 0 only if the process is reversible. Okay. And a way to think about this in terms of what is a reversible process. I mean, the book has a big, fairly complicated explanation of reversible and irreversible processes. And so I just like to kind of think in more simple terms, personally. And so then what I think of is that if the process is reversible, then that's a situation where mechanical energy is conserved. And so the implication here is that there are no dissipative forces. So that means, no friction, no air resistance, none of that. So if that's present, if that's true, then we can keep the entropy the same. The entropy doesn't change, and so I think that's generally a pretty good way to do this. The second law of thermodynamics is usually referred to this is referred to as the arrow of time. Okay. And the reason for this is because if you were to take, and film any physical process, such as, I slid the little whiteout marker across the table and comes to a stop. Okay. then we would talk about how I did work on the marker to make it, increase its kinetic energy. Net work is delta K. Increase its kinetic energy. And then as it slid, friction between the whiteout marker and the table essentially did negative work, and caused the mechanical energy to decrease to zero as it comes to a stop. And it basically converted that energy into an increase in thermal energy in the atoms and molecules on the table and the atoms and molecules in the bottom of the marker, right? As you know, pull them across and they snap back into place, they all vibrate around and you get, an increase in temperature, okay? Thermal energy or internal energy, as we would call that. Now, if we were to film that and then reverse it, then what you would see is that the marker and the table would become cooler as it speeds up and then hits my hand. Now, what we know is that that process doesn't happen, okay, in nature. But the process of having both the marker and the table cool down as it speeds up doesn't really violate any other law of physics other than the second law of thermodynamics. Because what we did was we took ordered energy, my work, into kinetic energy of the marker, and then as it slid to a stop with friction, then it converted that energy, that mechanical energy, into thermal energy, which is more disordered. And if you go the other way, then you basically convert disordered energy into ordered energy. And you would have decreased the total entropy of the universe in that process. Now, remember when we talked about the universe, then there was that, the world's easiest Venn diagram, right? Where we have our system, the environment, and the universe. The universe is what they're talking about. Because we talked about that, Monday. And so we can, like I said, we apply this to all sorts of things. And like I said, it will tell us, if we were to reverse the film, which one of those ones is the correct one, which one is reversed and which one is the correct forward version. And so, like I said, they usually refer to this as the arrow of time.